we have come to the end of experience 1 here. And we're looking at revisiting Coulomb's law a little bit and how it can apply not only to attractive forces within an atom, but attractive forces between charged ions in an ionic compound. And so we kind of mentioned this whole time that Coulomb's law is an equation. It calculates the energy change needed to either separate the charged ions or the energy released when the charged ions come together. But you will never have to calculate anything using Coulomb's law. We're just going to use it to kind of gauge the degree of attraction between oppositely charged particles, here, ions. Now, in general, there was like a little Q1 and Q2, and then there's R squared in the denominator, where Q1 and Q2 represent the charges of the ions. And so in number 9, we are looking at an ionic compound of aluminum and oxygen, also known as corundum. It's in sapphires and rubies. It's a mineral that's really, really strong. Okay, so let's think about the charges on aluminum and oxygen. Aluminum, oh boy. Aluminum has 1, 2, 3 valence electrons. So we're trying to get to 8, probably still easier to lose 3 than gain 5, right? So if I lose 3 electrons, but I don't lose 3 protons, I would have 3 extra positive protons, and they're telling me here are the charges, +3 or 3+. Same thing. I've just known since I was a little girl that I've written my charges as +3. But if you're into 3+, it's the same. Then they also tell me that the oxygen ion is -2 or 2-. Yeah, because oxygen's got 6 valence electrons. It probably now is easier just to gain 2 for a -2 charge. Those are some pretty high charges. Usually we've been looking at ions that are like +1 or -1, +2, -2. Here we've got a +3 and a -2. In the end, we're supposed to say how Coulomb's law can be used to explain how the bonding in aluminum oxide influences its properties, that it's one of the hardest known minerals. So these ions must be packed really tightly together. Well, number 1, I might say that the charges are really high. There's large charges, and those large charges are going to lead to really strong attractions. Then number 2, the second thing we look at, R in the bottom, is the radius, and that refers to the size of the atom or the size of the ions. Okay, so here I'm looking at aluminum and oxygen. Okay, so aluminum has 13 electrons. It's in the 3rd energy level, but we're going to lose those outer 3, so that we're really just talking about then 10 electrons, which would be like a full 2nd energy level, which is actually going to be really similar to oxygen. Oxygen is in the 2nd energy level, the 2nd row, and he's going to gain 2 more electrons. These ions are both going to end up with 10 electrons. When you take their charge into consideration, 10 electrons puts me in the 2nd energy level, which is a pretty small ion, because, I mean, think about it. Hydrogen and helium are probably not likely to form a lot of ions. I mean, for sure not helium. And we'll look at hydrogen a little bit more in the second half of this unit. Sometimes hydrogen can form a few ions, but often it does something different. So really, if there's not a lot of choices for ions that only fill the 1st energy level, then 2nd energy level is about as small as we're going to get. So why is this such a hard mineral? In a nutshell, maybe we would say large charges and small ions. those large charges, the +3 and a -2, will create a really strong attraction. And then because the ions are pretty small, they'll pack really tight. So we've got tiny particles packed really tight together, and they'll be highly attracted to each other. That should lead us to a really strong bond and then a really hard or really dense mineral.